Welcome to the IFS CAD adapter operation video. In this video, we will show the basic functionality of the IFS CAD adapter from the end user perspective. If you are not already familiar with what CAD adapter is, please see the CAD adapter overview video. If you are not familiar with the 3D CAD, please take a look at the CAD adapter CAD concepts video. You should also be familiar with basic IFS concepts such as documents and engineering parts. Now let's see how all this looks in practice. In this video, we'll use SolidWorks, but the principles are same for all supported CAD systems. The CAD adapter is an add-in that executes within the address space of the CAD system. And as you can see, the CAD adapter user interface is integrated into the CAD user interface in the form of IFS applications many. Now let's load a simple part. This part is bolt in this case. At this point, most of the CAD adapter user interface is still grayed out because we are not logged on to the IFS yet. So let's log on. We provide IFS username and password, as well as the name or IP address and port of the IFS server. The password can be encrypted and stored for future logons by ticking the Remember Password checkbox. Now that we are logged on to IFS, several CAD adapter options become available. The first one we are going to use is check-in. Our goal at this point is to store to the IFS server the CAD part that up to now existed only locally. Since a single CAD part maps to an IFS document and an IFS part, we must tell the CAD adapter which document and part numbers to use. We could supply our own or just accept defaults, which is what we're going to do here. At this point, the CAD part is marked as being in the conflicted state in the check-in dialog, which in other words means the CAD adapter cannot proceed on its own and must instead rely on the user to supply the missing information. And let's perform the initial association. And let us just accept the defaults. As I already mentioned, we are using the default document number offered here. So we have just supplied the document number. Let's apply the part number as well. And let's accept the default part number here as well. You can see that the CAD part is no longer marked as conflicted. It is now in so-called dirty status, indicating that there is still a mismatch between local CAD data and IFS data, but no more user intervention is necessary to synchronize the two. When user clicks the check-in button, the CAD adapter can perform the synchronization on its own. So let's do that now. By the way, we can optionally choose to generate the viewable in the process, so let's pick that. At this point, the check-in has finished and the CAD file has been physically uploaded to IFS and stored in the IFS document. What we expect to see in IFS is the following. First, IFS document physically containing the CAD file. Second, IFS engineering part. And third, connection between the two. So let's go to the IFS user interface and see if we really got what we expected. Let's search for the document that was just created. And we're searching for the document number bolt. And let's open the details of the found document. In the File Refs tab, we can see three file references. One is the CAD model itself, The other is the viewable that has been generated during the check-in. And finally, there is a special file used by the CAD adapter to keep certain extra information about the CAD model, and should generally be ignored by the end user. In the Objects tab, we can see connection towards the engineering part, and if we open it, we can access the engineering part navigator, where this connection between engineering part and document can be clearly seen. So that's how a simple non-generic part is represented in the IFS. Now let us try checking in the whole assembly. First we open the assembly in CAD session. And invoke the check-in option once again. And let us expand that check-in tree. As you can see, the check-in tree follows the assembly structure, and the bolt part is already mapped to IFS. So we don't really have to do anything for it to be participating in the check-in. However, the nut part and the nut and bolt assembly are not yet mapped to IFS, as indicated by their conflicted state. We could just select each of the conflicted items and map them to IFS one by one, but there is a more practical method in case you have a big assembly. It's the AutoMap dialog. The AutoMap, as its name suggests, is an automated tool for performing the initial IFS association in a bulk manner. There are tools for setting multiple items to the same value. For example, we could connect both IFS parts to the same technical class, like this. Or we could clear the default document and part numbers and let the IFS generate them for us, like this. But we're not going to do any of that right now. We will simply accept the defaults. And the check-in dialog now indicates that the whole assembly is ready for the check-in. All CAD models are mapped to corresponding IFS objects, and there are no conflicted items left. When we click the check-in, the CAD adapter will physically upload the remaining CAD files and also create the necessary IFS connections that reflect the CAD assembly structure. So let's do that. What we expect to get in the IFS as the result of this check-in is the following. First, 3 IFS documents, 1 for the assembly and 2 for parts, connected together in such a manner as to reflect the CAD dependencies. Specifically, we expect the assembly document to be the parent of the remaining 2 documents. Second, 3 IFS parts, 1 for each CAD model. Again, they should be interconnected as to reflect the assembly structure. The connection between 2 IFS parts can include the quantity, and since there are 2 nut components in the assembly, the quantity of the corresponding IFS part-part connection should also be 2. And third, we also expect cross connections between IFS document and IFS part hierarchies. Let us go back to the IFS user interface and see what we got as a result of the assembly check-in. So let's search for the document number that we assigned to the assembly during the check-in, which is nut and bolt. And let us open the details about this found document. In the file references, we have a situation as explained before. We have the original file, CAD file, which is the assembly in this case. We have the viewable, and we have this special CAD adapter file. In the Consists of tab, we can see that the document connections that were created follow the dependencies at the CAD level. So since these two parts were referenced by assembly, the documents in IFS that represent these parts are connected with the document that represents the assembly itself. If we go to one of these parts, we can see the details about the part, and we can also go back to the assembly through Where Used tab. So let's do that now. And we are back at the assembly level. In the Objects tab, we can see that the IFS document is connected to the IFS engineering part. If we open that part and then open Engineering Part Navigator, we can see that the generated structure of IFS parts closely follows the CAD assembly structure. The consists of tab shows these part-part connections in detail, and we can see that the quantity is correct. The nut and bolt assembly references the nut part twice, and this is reflected in the quantity field in IFS. The document hierarchy that we saw through the documents consists of tab is unfortunately not directly visible in the part navigator, but we can see the cross connections between the part hierarchy and the document hierarchy. So this was how a simple non-generic assembly was mapped to IFS. Let us now illustrate the mapping of an assembly with the family table. We have loaded into the CAD session a simple generic assembly. This assembly has two instances, or configurations as they are known under SolidWorks. In the configuration 3 nuts, we have 3 assembly components that all reference the same part, which is nut. In this other configuration, one of these components is suppressed. So by switching between these two configurations, we effectively switch between different quantities in the BOM. When we invoke the check-in function, we'll see that the generated check-in tree is more complex than in the case of a simple non-generic assembly. Each of the assembly instances are mapped to a separate IFS part, which will allow this difference to be reflected in IFS. You'll notice that the check-in node called 3 nuts has a child nut whose quantity is 3, while 2 nuts has a child quantity 2, with a separate node representing the suppressed assembly component, which is not counted towards the final quantity. We map the generic assembly to IFS by associating it to a document number and then associating each instance with its own separate part number. So let us associate the assembly with an IFS document, and as before we will simply accept the defaults, including the default document number. The next step is to associate each of the generic assembly instances with its own separate IFS part number. And we will accept the defaults, including the part number 2 nuts. And we are going to do the same for the other generic instance. We don't need to associate parts, since we have already done that when checking in the non-generic assembly, so we are ready for the check-in. So let's do that. Let's go back to the IFS user interface and see how the generic assembly was mapped there. We're going to search for the document number that was used during the check-in, and that document number begins with generic, so we are going to search for that. And let's open the details of the found document. In the Consists of tab, we can see that the structure is the same as for the non-generic assembly. Document structure does not depend on the genericity of the CAD models. However, if we go to the Objects tab, we can see that the assembly's document is connected to two engineering parts. Each of these parts represents a separate generic assembly instance. If we open one of the instances and go to the engineering part navigator, we can see the structure of that instance, and we can see that the quantity is correct for that particular instance. On the other hand, if we open the other instance and go to the engineering part navigator, we can see that the quantity for that instance is different. That is, of course, because this instance referenced one more part compared to the last one. This way, we can have instance-specific bill of materials. So now that we have our CAD files uploaded to IFS, we probably want to continue to work with them and improve design. Before we can modify a CAD model, we need to check it out from IFS. And I'm going to start by demonstrating how to do that on a single part. The currently loaded part should be checked out from the IFS before it can be modified. So let's do that now. Let's go to the checkout option. And there are some options here that are related to assemblies. Let us just keep the defaults for now. And we here see the report about what is about to be checked out. We need to supply the new revision that is going to be created as a consequence of the checkout in the IFS. The first initial revision was A1 that was created during the initial check-in, and this checkout is going to create the document revision A2. And now the document is checked out and our CAD model is ready for modification. So let's modify it a little bit. Let's create a sketch on one of the faces and let's create some geometry there. Obviously this is not going to serve any useful purpose. It's simply going to demonstrate that we have changed the part. And now that we are finished with our changes, we can check the part back into the IFS. So let's do that. The part was modified but not yet saved, so we need to save it first. And as you can see, we don't really need to repeat any of the association steps. The part has kept its association information from the last check-in. The dirty status simply indicates that there is a difference between local and IFS data. And when we click on the check-in, these two are going to be synchronized. So let's do that. Every checkout check-in cycle produces a new document revision. So if we search for the NUT document, we can see that there are two revisions in the IFS. The first revision was created during the initial check-in, and the second revision was the result of the checkout check-in cycle that we have just demonstrated. Each revision contains the file in a separate point of time. And this is the way how we preserve the full history of changes. This can be viewed as a kind of undo mechanism on steroids that continues to work even if we close our CAD session or restart the machine. It can be accessed from the get operation by specifying one of the older revisions, in this case A1. And we get this report that we are about to get the revision A1. Let's do that. We get the warning that the newer local file is going to be overwritten by the older file downloaded from the IFS. But let us overwrite it anyway. And this is the older revision. Of course, we can go in other direction and retrieve the new revision as well. So let's go to the get option again. But this time, let's pick the latest revision. We get the report about what is going to be done. Let's click OK. And this is our newest revision. This way, we can freely go forward and backwards in time. Let us modify the part again. We can do this in a standard way by checking out. And let's create some new geometry there. Like this, for example. But maybe now we realize that this is not such a good change. And we don't really want to put that change into the IFS. So we can simply undo our checkout. We get the warning that we might lose some editions, but this is okay. We actually want to lose these incorrect editions. And we have undone our checkout operation. Of course, the same mechanism works with the assemblies as well. So let's open the nut and bolt. And let's check out the assembly and its constituent parts. Let's apply the same revision for everybody. Let's make it A3. And now we can modify both the assembly and its parts. So let's drag these parts around just to modify the assembly a little bit. Something like this, for example. And let's modify the individual parts. For example, let's make it a little bit rounder, like this. Now let's go back to the other part and let's lose this extrusion here and make it slightly rounder as well. For example, like this. And as you can see, we have modified the assembly by dragging the parts, and also we have modified the parts themselves. So let's check in the changes back to the IFS. As you can see, there is nothing to be done here. We simply get the report that certain things are going to be uploaded to IFS. So let's do that now. As with individual parts, the history of the whole assembly is preserved, and we can easily go to the older revision should we ever need to. So let's demonstrate it shortly. Let's get, say, revision A1. And that's our older revision. We can also get the new revision by specifying the latest revision. And as you can see, we have the full power to go forward and backwards in time. Of course, CAD adapter can be used by a whole team of engineers, so let us demonstrate some of the aspects of the multi-user work. Let us pretend that we have another user that works in parallel with our old user. So let us log on to the IFS as a different user, and let us try to find the assembly that was checked in by a different user and then bring it back to our local file system. So let's find the document with the document number nut and bolt. We want to retrieve the newest revision, so this is okay. We could also choose to retrieve the older revision if you wish. And let us retrieve it to a new folder. And let's call the new folder nut and bolt 2. We get the report about all the connected documents that reflects the dependencies between assembly and its parts. And we can also check this checkbox here, which would cause the downloaded assembly to be immediately opened in the CAD session. And we have our assembly. The important note is that the whole assembly, including the top assembly and all of its parts, was downloaded and then opened in the CAD session. This works no matter how many levels the assembly has. And this second user can now proceed with modifying the CAD files in a normal way. We go to the checkout and we are going to check out the assembly and all of its parts. Let us now modify the assembly by, say, creating a new component. And let us modify the parts as well. So let's make this part a little bit more edgy. We are going to delete the fillet and create a chamfer in its place. And we are going to modify the other part as well. And we can simply check in the whole assembly in a single step. All the check-in items are already associated to the IFS, so we can simply click the check-in. Now that the second user has checked in his or her changes, the first user can get them by invoking the get option, of course, and can normally continue to work with them. For example, modifying would be done in a standard way by invoking the checkout option. Now, if the second user tries to check out the documents, he or she will not be able to do that because the first user is still holding the documents locked. So users are protected from stepping on each other's toes, so to speak, when working in a multi-user environment. And with that, we have covered the basic CAD adapter workflow, including operations such as get, check-in, check-out, and undo checkout, as well as find, combined with the retrieval of the CAD models from the IFS. In addition to that, the CAD adapter also covers mass and material mapping, manufacturing data, new part number generation, recursive document approval, etc. Please refer to the CAD adapter documentation for more information. The main benefit is one-click check-in. Customers don't have to worry about synchronizing IFS objects and connections with the CAD data. CAD adapter automatically does that for them. By making the mapping between CAD and IFS automatic, users can rely on accurate, up-to-date IFS data. CAD adapter promotes team collaboration and sharing of data and supports the environment where multiple CAD systems access the same IFS database. That concludes the CAD adapter operations video. Thanks for watching.